Good morning, class. Welcome to the physics online classes for class 12th. In the last earlier few sessions, we were seeing about the chapter moving charges and the magnetism. That is the first part of that. And in the second part, we were going to see about the magnetic material, that is magnetism and the matter. So this is the last session for your moving charges and the magnetism. We will see just a quick revision that what are the topics which we have learned in this chapter. Firstly, we have seen about the moving charges, and we have read that the moving charges possess electric field as well as the magnetic field. But firstly, it was experimented by a scientist named H.C. Oersted, and he gave his experiment name as Oersted's experiment. We know that every magnet possesses the magnetic field around it, and what that magnetic field means is it is a range around the magnet till which an object will influenced by the force of the magnet. So till that range the object can be influenced by the magnet, so it is said to be the magnetic field, right? And similarly, electric field was also there, that till the range around the electric field, that which the object will be influenced by the force of the electric, and the lines of these forces were seen by the magnetic field lines and the electric field lines. What were the electric field lines? It was seen with the straight lines, and the arrow was shown by the direction, which was always from positive to the negative. And in the magnetic field lines are shown with the help of the curved loop. So closed curved loops are used in the magnet. And what does the direction shows us? That the magnetic field lines moves from the north and diverges into the south direction. So it moves from north to south, and again it is stopping at the south, but inside the magnet it is moving from the south to the north. Okay, so what's the direction mean? That it is moving from north to south in the outward around the magnet, and inside the magnet it is moving from south to north. So together, if we see the southward and the inward direction together, we can say that the magnetic field lines is in the form of the closed curved loop. So electric field lines are shown with the straight lines, and the magnetic field lines are shown with the curved loop. And what was the first experiment that it shown that the moving charges possess the magnetic field? That was the Oersted's experiment. Okay, so what he told, that we know that an instrument which shows the magnetic field or the influence of the magnetic field is the compass. And what it shows it is used for the showing the direction, right? North and the south direction. And what it helps to be, whenever we keep the compass, the needle is present in the compass, which is colored as a red and half is as white, and some it is colored as a black also. So but the red arrow shows always towards the north, so it points towards the north direction. And whenever the compass is kept anywhere, it just align itself in the north and the south direction. And why it is doing? Because our earth is just behave as a magnet, and there is a geographical north and the south of the earth. So these arrow, it just align itself in the direction of the north and the south of the geographical earth's north and south direction. So now this needle will be showing the south and the north direction according to the earth. And similarly, now what he did, that he took a compass and connected it to the terminal of the battery. Now what he did, he just connected to the battery, so the current will be applied, right? Because whenever the terminal is connected, then the potential is given through the wire, and this potential is allowed to movement of the charges, and these moving charges is said to be producing electric current. Okay, so here when we are connected this compass to the terminals of the battery, we have seen that this needle of the compass is also moving. What does it mean? That the needle of the compass only move due to the magnetic field experience, right? Whenever it experiences the force due to the magnetic field, then it starts moving. Because in the simple way, if we are keeping it in the compass at anywhere, it just experiences the force of the geographical north and south of the magnetic earth's behavior. But if it is now moving, then it is due to the electric field. Now what we can say, that electric field is the movement of the charges. So these movement of these charges is allowing the compass needle to move. So we can say that the moving charges possess the magnetic field. And we know that the moving charge is there, then it is possessing electric field also. Okay, so this moving charges is allowing the magnetic field also. So similarly, when he reversed the terminal of the battery, he found that now the needle is deflecting in the opposite direction. When he did the experiment in the first time, the needle is moving towards the east direction. Now when he converted and reversed the directions of the battery or reverse the terminals of the battery, he said that the needle is also moving in the different direction. So this deflection is due to the electric field of the charge. So these moving charges is applying the magnetic field, and this what means that the moving charges, it produces the magnetism. So this is the relationship between the electric field and the magnetic field. So the Oersted experiment was the first experiment given by the H.C. Oersted to tell or relate the electric field as well as the magnetic field. And now what the direction means. Here the first thing, it is given as Ampere's swimming rule. It is used for this compass itself. This can be understood by the Oersted experiment better, because whenever the current flows and the magnetic needle or the magnet is kept there, then the magnetic field is produced around the magnet, and now the magnetic field is produced around due to the moving charges. If the magnet is not there, then the moving charges is producing the magnetism. Now what it does, if the current flows from the south to the north direction, it is moving from the south to the north direction, then what the needle will do, the needle will try to deflect towards the south direction. So this was a rule given by the given as Ampere's swimming rule, and similar it is also said to be the snow rule, because to read or to just by heart the direction, we use the snow rule. And what the snow means, S represents the south direction, N represents north direction, and W represent the west direction. What does it mean? Whenever the current flows from the south to north direction, then the compass needle will deflect towards the west direction. So this was the rule given by the snow. This was the snow rule. Okay. So here this is given as a swimming rule, because imagine a man who swims in the direction of the magnetic field. We are just imagining a person in the direction of the magnetic field. The magnetic field is not produced in the swimming. But if we think that the magnetic field lines is in the direction according to the direction of our swimming, then what we will do, then our hand will move towards the first to the west direction. That is, our left hand will move first, or our hand will deflect towards the west direction. So here we can say that if the magnetic field is there and the current is produced or the moving charges is produced as the magnetism, then if the current flows to the south to north direction, then the needle will deflect towards the west direction. Okay, and these direction of the magnet and the electric field can be better understood by the right hand rule and the screw rule. If we just imagine that the screw moves in the forward direction, and if we imagine that the screw is taken by the right hand and the current is taken in the direction of it, then the directional rotation of the screw gives the direction of the magnetic field lines. What does it mean? Like if we consider that the current is in the direction of the needle, now needle is kept in the wall, and what we used to do, and we just have to rotate it, right? And that means that the rotation gives us the direction of the magnetic field. Now if we rotate in the left direction, then what it means, that it is rotating in different direction, the current direction will be at the outside, because if you move in the right hand direction, if you move the screw in the right hand direction, then it move inwards. What does it mean? That the current is moving in the inward direction. So the electric field lines will be in the inward direction towards the plane of the paper. And now if it moving outward direction or in the left direction, then the screw will come outward. What does it mean? That the current field is moving outward to the plane of the paper. But the magnetic field line is always a closed curved loop, so it shows the rotational angle of the screw. And similarly, we use the another rule also, that is the right hand thumb rule. This is also known as the curl rule. During using our right hand, we take the electric field in the direction of the thumb, and we take the magnetic field lines in the direction of the curls of the finger. So if we imagine that the thumb direction shows the current field direction, then what the fingers of the remaining fingers will do? What are the fingers? That the curls. It will be moving inside, or it takes a curved loop, right? It moves in the curved form. So the curl of these fingers shows the magnetic field direction. Okay, so this is the easiest rule which we can use for finding the magnetic field and the electric field direction. Okay, after that, this is the Biot-Savart law, which is also known as the Laplace law. This law was given by the Biot and the Savart. Okay, so Biot and Savart, what they did, they have told about the magnetic field at some point kept at any distance from the current carrying loop. We know that the current carrying loop carries the magnetism also, because current carrying loop will have the moving charges and they will possess the magnetic field. Now if we have some particular point P and we have to find the magnetic field at that point P, then it is kept at some distance from the current carrying loop. So what is the magnetic field at that point P due to this current element of the current carrying conductor? But throughout the wire we cannot find out. So by taking a small current element, he find out the magnetic field at the point kept at a distance r from that element, and let the element of the wire be dl, because the length of the total wire is l, then the current element of that wire is taken as a dl. So what is the distance between this dl and the point P is taken as r. So what the magnetic field of that small current element is taken as, it will be also the small element, so it is taken as dB, because magnetic field is denoted by the letter B. So it is a vector quantity and the unit of V is Tesla. So B is of this small element due to this small element of the current is taken as dB. So what this dB depends on the current also, that is dB is directly proportional to I. It will depend on the length of the wire also, that is dl, or the current element dl. It will depend on the angle between the distance of this from the point P to the current element. So distance between the P and dl is given by r, and the angle of these r and theta, r and the current element is given by theta. So it depends upon the theta also, but it is a vertical component, so it will be taken as sine theta, and it is inversely proportional to the distance, because we know whatever the distance will increase, then the magnetic field will also decrease, because cannot the magnetic field range will increase along with the direction and the distance. So as the distances increases from the point, the value of the magnetic field also will be decreasing. So the magnetic field at the point P will increase only when it is near to the current elements. So what the formula was given by the Biot-Savart was dB as is equals to the mu naught upon 4 pi I dl sin theta upon r square. Together we are remaining these 4 points, we can get as ideal sin theta upon r square. By taking out the proportion, we get the proportionality constant, that is mu naught upon 4 pi, where this mu naught upon 4 pi defines the permeability. Okay, absolute permeability. What does permeability means? That what are the means you can say that the permittivity was the obstacle for the current. So the permeability is the allowance of the current through the magnetic field. So permeability is given by mu naught upon 4 pi, and the value of the mu naught upon 4 pi is 10 to the power minus 7, because mu naught is 4 pi into 10 to the power minus 7. So mu naught upon 4 pi can be written as 10 to the power minus 7. Okay, CGS unit is Weber per meter, and for SI unit is Tesla for the magnetic field B. Okay, so here mu naught is equals to dB is equals to mu naught upon 4 pi ideal sin theta upon r square. Is this in scalar form, and if you take in the vector form, this is sin theta, so it can be written as a cross product of I and dl, or ideal cross r, and at the down it will be given by r cube. So this is the vector form of the Biot-Savart law. Similarly, we have seen the magnetic field due to the straight carrying wire, current carrying wire, and a circular loop also. And we have to find a magnetic field at a point P due to this straight current carrying wire and the straight current carrying wire of a circular loop also. So we have to point a magnetic field at a point. So we will be using the formula of the Biot-Savart law itself. Okay, so we have assumed a point P where we have to find the magnetic field. Let the point P is at the distance r from the current element dl, and the angle between this r and the dl will be given as theta, and we are taking the ends of the wire to be A and B, and the distance from these ends be the x and y, and the point P from the end A and B will be taking an angle phi 1 and the phi 2. So we just have to replace here sin theta, dl and r. So we have to take out the values of dl cos phi, that is sin theta will be changed into the cos phi, and r value and the dl's value. So by taking this derivation, we can find out the values, and we'll be putting the value of the sin as well as the l and as well as the dl. So on putting these values, we find out that the magnetic field at the point P due to the current element L of the straight current carrying wire is taken as mu naught upon 4 pi I sin phi 1 plus sin phi 2 upon 4 pi A. Okay, so if the wire is infinitely long, then the value of sin phi 1 and phi 2 will be taken as 90. One will be taken as 90 and one will be taken as 0. And if it is finite, then one is taken as 0 and one is taken as 90. But if it is infinitely long, then both will be taken as 90 degree. From there, we will be getting sin phi 1 will be 1 and sin phi 2 will also be 1, and 1 plus 1 will be 2. So it will be mu naught upon 2 pi I. So this relation of the magnetic field at a point P due to the straight current carrying wire, and the magnetic field due to the current carrying circular loop. So circular loop, we can, if we have a direction of the current is taken as I, you can see here that is rotating circular loop is having I in the direction. If we see the direction of the magnetic field, how it will be, if we are keeping our thumb in the direction of the current, then the curls of the fingers will be around the circular loop, so the magnetic field loops will be getting throughout the wire. And if we have to find out the point P, the magnetic field of the point P, due to the axial position between the center. If I take a center position from the circular loop, then what is the value of the current at the point P? Magnetic field at the point P due to this current carrying loop is also found with the help of the ideal sin theta upon r square, that is Biot-Savart law itself, because he told it was the first law which tells us about the magnetic field at any point P which is kept at a distance from the current element. So whether the shape changes, but the law will be used by the Biot-Savart itself. So from here we got it the mu naught upon 4 pi I dl upon r square. But we know that here from the figure you can see that we are taking the two components of the magnetic field. One is the vertical and the horizontal component, dB sin phi and the dB cos phi. All the dB cos phi are formed in the opposite direction, so they will be cancel each other. But dB sin phi together, all the vertical components are through the axial position also. So we can say that the magnetic field at the point P is due to only the vertical component of the magnetic field, that is dB sin phi. So the sum of all the dB sin phi will be given as the magnetic field. So B will be equals to the integration of the dB sin phi, which is given at mu naught upon 4 pi I dl sin theta upon r square. So sin phi is taken as 2 pi a upon a square plus x square to the power 1 by 2. Together it is written as 3 by 2. So this is the relation, that is B is equals to mu naught I a square upon 2 a square plus x square 3 by 2. Okay. So this is the relation for the current carrying loop to find out the magnetic field at any point P. And if it is kept at the center, then the value of A will be 0. Then it is mu naught I upon 2a. And if x is very small than that of the x is very large than that of the A, or A is very small than of the x, then the A will be neglected. Then only x will be present in the equation. So this is the equation of the magnetic field at point P due to the current carrying loop. Okay. If the current carrying loop is present at the center of the loop, then the sin theta will be taken as sin 90. It will be 1. So mu naught I dl sin theta upon r square is taken as mu naught I dl upon 4 pi a square. So integration throughout the center it will be same, because it is a center, then the throughout the curved loop will be as the same. So integration of the dB will be given as mu naught I upon 2a. So after that we are taking the topic Lorentz force. And what is the Lorentz force is, we know that the moving charges experiences both. All moving charges produces both the fields, that is the magnetic field as well as the electric field. But if it is stationary, then it is possessing only the electric field itself. So the force experienced by the stationary charge is given as the electric field, and was the electric force was given by QE, that is the charge experienced by the electric field experienced by the charge, or charge experienced per unit field. So force is given by QE, that is charge experiences the electric field E. So it is given as QE. And the force experienced by the particle in the magnetic field is given by QVB. Now V is the velocity of the particle, because a moving charge will possess a magnetic field, so velocity is needed. So V and B is the magnetic field, so the charge experiencing the magnetic field with the current itself. So it is given as QVB, the magnetic field. And now we know that what the Lorentz force, it is the force that is comparing to the magnetic as well as the electric field of that charge, because the moving charge will possess both the fields, electric and the magnetic. So the charge will experiencing both the forces, that electric and the magnetic force. So what we can write it as, it is the charge will experiences both. It can be written as QE plus QVB, and together the combination of these two forces is said to be the Lorentz force, because it was first given by the Lorentz. So this is the relation for the Lorentz for the QE plus QV cross B. It is given by F is equals to QE plus V cross B. From here we can say that the value of the motion of the charge, that is V, force and the magnetic field, should always be perpendicular to each other, which is given by the Fleming's left hand rule or the right hand rule. The three of them should be perpendicular to each other if we are stretching them mutually perpendicular to each other. The thumb finger always shows the force and the middle finger always shows the current, but here the current is taken as the velocity of that charge, because it is a moving charge. So V will be given as the electric current. Instead of electric current we will be using V, and the magnetic field is given by the pointing finger. Now the force experienced the current carrying conductor in uniform magnetic field. So the magnetic field is throughout the same. So we can say the force experienced by each electron in the conductor is given by V into B, that is V cross B. We have seen now only Q is equals to V cross B, but the electron is given by minus E because the charge of electron is minus, and drift velocity will be taken. And the next thing, so the force experienced by the particle in the uniform magnetic field is given by I V cross B, but here the L will be taken because due to the element of the particle, elementary particle of that wire is taken as dl. Okay. Now, if a particle is kept in the uniform magnetic field, it will experience the two forces, and these couple of forces is said to be the torque. And what the torque is given by, it is represented by the letter tau. Okay, so tau is depends on the two forces that it allows to move. So both the forces will be acting on the current carrying loop, that is the rectangular loop is used, and similar this function or this principle is used in the galvanometer also. So these current carrying loop, that is the rectangular loop, is kept in the uniform magnetic field. Now what is magnetic field lines will do? They will try to turn this, or will try to rotate this loop, rectangular loop. So the two forces acting on the, because to rotate any object, the two different opposite direction forces should be act on an object. These two opposite forces acting on an object is taken as the torque, and this torque is a couple of force which is given as the tau. So the tau is given as, it depends on the number of the turns, that is on the rectangular, the number of the turns of the bond of the wires of the copper wire on a surface, that is given by N. I is the current flowing on that particular coil, and A is the area of the coil, and B is the magnetic field. So what is the torque is given by NIAB sin phi. Here the sin phi tells us the cross product, so it can be given as NIA cross B. And what this I and A was, I and A is the current flowing through per unit area of that wire. So the current flowing through the area is given by the magnetic dipole moment. So this is the torque. Similarly, this principle will be using in the galvanometer also. So galvanometer is a device which is used for measuring the small current in the device. It is a very sensitive device. It is used for only measuring a small currents. And we have seen this in the lab also. If you want to see the instrument, you can see the lab, that the pointer is used, which used to deflect with the current, and it is, if we drag it more and more times, it will get the heat also very fastly, you can say, and it gives the deflection very rapidly also, because it is a very sensitive object. It can be due to the current as well as due to the voltage. So we have seen the current sensitivity also, and we have seen the voltage sensitivity also. Here we are using a rectangular coil which is placed between the horseshoe magnet and the north and the south pole. What they used to do, this different poles allows the body or the rectangular loop to move, and this movement is in the form of the rotation. So the two different forces and the different directions are acting on the loop, which allows it to move, and these couple of forces is said to be the torque. So the torque is acting on the rectangular loop to move it. So what we can say, this is movement of the torque is connected to the pointer, which is suspended by a wire, which is a phosphor bronze wire. Okay, so this is a terminal which is taken as a torsion head, and the mirror is also used. And now this poles of the magnet, the phosphor bronze wire, is allowed to move the pointer, and this pointer shows the deflection of the current. So this deflection will show the measurement of the small current passing through the rectangular loop, and the rectangular loop is taken by the bonds of the copper wire. So the copper wire turns will show how much the turns will be, the number of the turns will tell about the current also. So the current is directly proportional to the number of the turns. The number of turns will increase, and the current will also increase in the loop. So it is taken as torque is given was in the last derivation. You have seen that it is NIA by sin theta. So here similarly NIAB sin phi. So here the torque is taken in the one direction, then it will one rotate, then again it will come back. So there will be retorsioning. So torsion is taken as the opposite direction. It is given by the retorsion, and with an angle it moving in the upward direction forward, and it will again backward it will move with an angle, and the angle is alpha. So what it can be given as, torque is taken as a twist of angle given by alpha. So torsion is coming upward and the backward direction, so it is taken as the retorsioning torque. It is given as T is equals to K alpha. Okay, so from here there you can find even the deflection of the galvanometer for the current sensitivity as well as the voltage sensitivity. Okay, you can better understand through your books also. And after that we have seen the solenoid and the toroid both have the same magnetic field, but the similar thing was that in the solenoid we used to take a hollow cylindrical shape, and we used to have a copper wire to be wounded over it. With the number of turns the current also increased, and if we take these solenoid bent into the form of a closed ring, then it is said to be the toroid. And the solenoid and the toroid both will have the copper wire as a wounded in the surface of it. So both will have some magnetic field, because the copper wire will have some current, so the moving charges will be there, so it possesses the magnetic field. So outside the surface of the solenoid as well as outside the surface of solenoid or the toroid, there will be no magnetic field. So inside the point there will be the magnetic field, and the toroid it will be throughout the ring. So it is given as B is equals to mu naught Ni, where N is the number of the turns and I is the current. So for both of them the expression will be the same for the magnetic field, mu naught Ni. And lastly, we have seen what the moving coil galvanometer was, and how can this galvanometer be converted into the voltmeter and the ammeter. We know that the galvanometer is a sensitive part, but it will require for both. It will calculate the voltage also, or the potential difference. It can calculate the current also. So can the galvanometer be converted into the ammeter as well as the voltmeter? How can we convert into? By, if we are having the small resistance, then it can just measure the current through it. If you are having the small resistance, the current flowing will be more, because resistance and the current are inversely proportional to each other. So galvanometer can be converted to the ammeter by just taking a small resistance through the shunt. And what the shunt means, we are taking a resistance wire and connecting it to the galvanometer in the parallel connection. So the potential difference across the galvanometer should be more than that of the current, and the shunt resistance should be equal. So what we can say, that both are in the equal, and the current should be taken should be more, so the resistance should be small. So from here we have find that the shunt resistance should be equal to that of the voltage. So S is equals to Ig and capital G and I upon I minus Ig. It is given by the shunt for the ammeter, that is conversion of galvanometer to the ammeter. Similarly, if you are converting a galvanometer to voltmeter, the resistance should be very high, because voltage is directly proportional to that of the resistance. If the voltage increases, the resistance will also increase, and we have to calculate the potential difference. So resistance should be of high value. So potential difference across the load resistance is that of the galvanometer. So it is the sum of the galvanometer potential difference and the potential difference across the resistance also. So Ig and G plus R. So current through the galvanometer and the galvanometer potential difference. So R is given as V upon Ig into G, where G is the current through the galvanometer and capital G is the potential difference through the galvanometer. So this is how we can convert the galvanometer to ammeter as well as to the voltmeter. So we can even practically in the labs also, you can, if you are not having an ammeter and the voltmeter, then we can use galvanometer also through the ammeter and the voltmeter. Just we have to connect it in the parallel and the series connection, then we can use it as a ammeter or the voltmeter. Now what is the difference between this ammeter and the voltmeter? We know that ammeter is a device used for the measurement of the current, and the voltmeter is a device which is used for the measurement of the potential difference. So ammeter should have the low resistance, because a current is inversely proportional to the resistance, and the voltmeter should have the high resistance because it is inversely proportional to the resistance. So voltmeter is a high resistance instrument and the ammeter is the low resistance instrument. And we have seen the instrument's resistance also, that resistance in the ammeter is given by S, G and I plus Ig. So G S upon G plus S. And resistance in the voltmeter is given by sum of the galvanometer potential difference as well as the potential difference across the shunt resistance. Yes, the ammeter should always be connected in the series, and the voltmeter should always be connected in a parallel condition. Okay, so resistance is less than that of the galvanometer in the ammeter, and the resistance is greater than that of the voltmeter, because in the voltmeter the potential difference is directly proportional to resistance, so resistance should be greater than that of the galvanometer. Okay, so range of the ammeter cannot be decreased, but the range of the voltmeter can be possible to decrease the value, because we can just change the potential difference across the galvanometer by increasing it. So we can just adjust the value of the voltmeter, but we cannot adjust the value of the ammeter when we use the galvanometer as ammeter and the voltmeter. So this is the quick revision for your chapter which we have learned, and these are the topics according to the CBSE syllabus which have not been deleted in the chapter of the moving charges and the magnetism's first part. So in the next session we will be trying to solve the numericals related to this chapter. So thank you class, and the next class we will be seeing the numericals, and after that we will be starting the new chapters with magnetism and the matter. Thank you.